get started. I just uploaded this yesterday for, so today will be basically my last lecture, right? And my plan for today is to do a review of sort of a comprehensive what I talked about in the past, at least this semester, okay? So this is in a PDF version that I uploaded on Moodle. And again, these are the slides that I have gone through in the past, and then I sort of pick up some of the important, kind of highlight, and then put it into a review document. So whatever today that I'm going to talk about is going to be show up in your final exam. So I already put up the final exam, the test questions. So that will be 100 minutes of a comprehensive closed book. You can use your calculators, you can use your electronic dictionaries, but it's a closed book. And these are the questions that I have covered for today. Okay, so today's class, I believe, is the most important, if not for you, if you're gonna take the final exam, right? So the final exam costs you 20% of the total entire grade, and then the rest of it is 80% of your document, your review paper, right? Draft paper or review paper. So one other stuff is I also have go ahead and then give out the homework too. So most of you basically is as long as you submit it, I give you 4 marks. So today, if you can do me a favor, is how about at the end of the class when we're having a break, go ahead and check on Moodle and check if you have all the grades that come in. So by this point right now, the grade that you are missing is just the comprehensive exam, that score which you haven't taken, and your tone paper. Okay, so that's the score. So there's only 2 scores you're missing. Otherwise, you should have everything covered. Okay? Okay. So with that, do you have any questions so far? No? So next week, again, we have Dr. Q that's going to come back and talk. So I'm going to leave that as optional. If you want to join, that's fine. And then next, let me check out the time right now. So. So today is May the 20th, right? So we will have our final exam on June the 3rd. Okay, so make sure you bring, well, it's a closed book, make sure you bring your, if you want to bring your electronic dictionary, that's fine. Or of course, bring your engineering calculators. I think we definitely have some calculation problems, okay? Okay, so let's begin our review sessions for today. Again, these are the review slides I pull up again. So what my plan for today is just again go through what I talked about in the past. So one of the questions I'm going to ask you, and of course it's not going to be the same question, but along that line is what is the surface energy on a designated surface plane, right? For example, right now I'm using the question of FCC crystal, right? So there's BCC, FCC, and then of course you have all different kind of plane that you can designate. So 111, and then you have 100 and 110. Right? So here is an example of if I ask you what's the surface energy of 111 surface plane in a FCC crystal, and please provide a explanation. Right? So here again, this is what I talked about. So the way that we calculate this is epsilon. So we need to know energy, right? So epsilon is the bond strength, right? So if a bond is broken, the energy of each of the atoms is half of it, right? So it's 1/2, right? Okay, so that's 1/2. So compare with the buck, every surface atom on 111 surface plane has lost 3 of the nearest neighbor atoms. You have the slide? Yeah. So for example, I'm jumping ahead, this is the 111 plane, and then the three atoms that's kind of dissociate, for example, we're choosing this one, that is dissociate with the designated atom, that's 3. So over here is, we compare block every surface on 1, 1, 7, lost 3 of the nearest neighbor atoms, right? So I kind of stated. So a few things, access is internal energy for each of 1, 1 surface atoms over an atom. In the bucket is, the way that we express that is 3 times half of epsilon, right? So we have 3 atoms and half, right? That's pretty straightforward. So if LS means the sublimation energy. So LS is the measure of the sublimation energy per mole, and for FCC structure. So FCC structure, the coordination number is 12, right? And 12 you times NA is the Avogadro number. So that's a constant number. Therefore, LS equals to 12 NA times half of epsilon, right? Okay? So over here is at the 1-1-1 surface, the solid vapor interface for the access internal energy for surface atom is, so access energy E, and I'm putting solid vapor, right? So again, is right now I'm just calculating the surface energy, right? So there's no liquid involved, right? So the surface energy, all it does is either it contact a surface or it contact a vapor like gas. So there's no liquid, right? So ESV, and I'm gonna go ahead and just make it more clear at the 1-1-1, that's the place I'm here the most, is 2/3 of epsilon, right? That's what I just wrote. And if you kind of organize that, you get 2 LS divided by 6 NA. Okay? So all I'm doing is using this, and then get a 2/3 LS divided by 6 NA. Okay, so pure assumption is I'm again considering only the nearest neighbor, right? That makes sense, right? So 3 atoms, that's the nearest neighbor. Second is the strength of the remaining bond still may change, right? We don't consider pressures or temperatures or anything, right? Okay? I believe if you look at the phase transformation, that book, there's tons of questions at the back of each of the chapters. So this is chapter 3, I believe, and talk about how you calculate each of the surface energy on a particularly designated plane. So again, the excess energy for surface atom on a 1-1-1 surface plane is, I'm gonna again rewrite that, is surface vapor at 1-1-1, again 2/3 of epsilon, 2/3 of LS divided by 6 NA. And if you simplify that, you get LS divided by 4 NA. Okay? So the excess surface energy per unit area, so that's excess units per unit is 1-1-1. So you express that as gamma equals to excess energy SV 1-1-1 times N. So N is the atomic number density, or what we so-call another way of saying is the plane density, which I'm gonna talk about a little bit more on the next one. So on the third section is N is the atomic number density 1-1-1. So if you get confused, what's the definition of this? Is the plane, the PD. Plane So plane density meaning that whatever the plane you're interest of is how many atoms occupy on that plane. Okay. So the short answer for FCC on the 1-1 plane is 4 divided by radical 3 times a cubic. So the way that I calculate this, if you review the previous recorded video or the slide, I already clearly expressed that you can draw atoms like this. And then you calculate this area. So this plane is on an FCC 1-1-1 plane, right? You overcross 6 atoms, right? And then the definition of plane density is PD. So PD, and then how many atoms fully occupied, on 1-1-1? So if you do a quick calculation, that's 2, right? So you kind of combine everything. So you have half of atoms, right? And then half of atoms of Q. And then you have, like, over here, you have somewhat, is it 1/6? Yeah, 1/6 of atoms, right? So I'm gonna quickly calculate that, you get 2, right? And then you calculate that area. So the area is 4 radical 3 times radical 2. So if you simplify that, you get this answer. One thing just keep, beware or, be cautious of is I'm kind of jumping a lot of steps. Here, I'm already assuming that you already know the relationship between the A and the R, either on FCC or BCC, right? So with that being said, these numbers you should be very familiar with, of FCC, BCC, or for say HCP, right? So I'm kind of jumping a lot of steps because the area in this area, you need to know the relationship between the A and R, okay? And this is how we obtain this area. That's the PD plane density here. So once you know that, gamma 1-1-1, again, I'm just rewriting ESV 1-1-1, and the plane density is 1-1-1. So ESV, we already know that. So when I say we already know that, is that relationship is right over here, right? And the N, that's the plane density, in other words, we also know that. Right? So what I'm gonna do is I'm gonna put these two and then multiply it, right? So LS 4-1-A times 4 divided by radical 3 times 1A cubic. So if you do your math and simplify it, you get 1 divided by radical 3 times LS and A squared. So that's, if you get your calculators, you should have your calculator for your final exam, is you get a number approximately 0.58 LS divided by N A cubic. Okay, so this is the surface energy for FCC 1-1-1 plane. Okay, so if you were diligent enough to calculate every surface energy of FCC, say 100, 110, and then you also do the same methodology that you apply on BCC for 100, 110, and 111, you can basically start to rank them from low to high or high to low. So then you have an idea what is the surface energies on a designated plane. So you have a more of an idea is, okay, which plane is more favorable, right? That has the lowest surface energy, right? And I'm gonna provide a little bit later on. I don't know if I provide that kind of ranking. Okay, so again, this today, I mentioned this is, anyway, so today is a slide, whatever I talk about it is important, right? So please spend your time, do your homework, study really hard about this, all right? Again, for your final exam, once you see these questions, it shouldn't be a surprise, right? This is very straightforward. I cannot express, it's like close to where I just dropped my final exam question in front of you, right? I'm almost close to that. Anyway, you still have to do your job. Okay, so if you guys copy this down, if not, this is the same slide previously. Again, the same stuff. Okay, so my next slide is, what I've done is I help you to organize what basically is the remaining atoms, right? So again, for example, this one is, I asked you about FCC 101. So with that, you need to know how many atoms is being lost, right? So for example, this is very straightforward. You have 3 atoms, right? So 3, I'm gonna go ahead and then mark that 3, right? And the reason why I know that is over here, it's very straightforward. You have the 111 plane, and the nearest you can lost is at the top. That's 3. That's connected to that atom, right? Now what I've done is I have go ahead and then help you put in a table here that if you look at this table, say FCC, the question that we just calculated is the plane 111, right? So the way that we do this is that we have a coordination. So FCC always have a coordination of 12, right? That's, everybody knows, okay? 12. So on the side that we're not eliminating, you have 9, right? So 12 minus 9, we lost 3, right? So if you look at, for example, 110, so if you look at 110, right? So the coordination is 12. Like, how do we get the coordination number? Is by designating an atoms and the closest similar distance of the coordination number of atoms. So we're at 12. So again, you have 12, right? And then the remaining one that still stay on the block is 7. So 12 minus 7 we get 5, right? And then that goes again, plane 100, we lost 4, right? So again, if my question would be ask you, hey, can you calculate the FCC surface energy of plane 110? You won't be timing 3 atoms, right? You will multiply 5 because you're losing 5. Okay, the same goes as plane 104, right? So you might ask me, like, how do I materialize that in my brain? So this requires some work. So this, I provide you a YouTube channel. This guy, actually, this scientist or this teacher, done a terrific job of constructing a 3D version of a crystallographic of FCC and BCC, and how you cut it, and then on one side, how many atoms is being lost, all right? So if it's just difficult for you to imagine, you can go ahead and then look at that video, and then it will very clearly tells you, okay? So I think BCC, 100, you have 8, right? So 8, 1, 2, 3, 4, 5, 6, 7, 8. That's even straightforward. You have 8, and then BCC is the base center cubit, right? So you have 8 as a coordination number. So on 100, if you kind of slice that, you have 4 on one side, and then you lost 4 on the other side, right? That's very straightforward. 110, you have 8 again, and then surface is 6, and then you lost 2, right? So I'm kind of leaving this, leaving another homework for you guys. Not homework, just for you to practice. Is that I didn't ask you about 111, right? So plane 111 on BCC. What is the CN loss? So what is that number? So you can play around with that. So this is an important slide just to know how many loss, coordination number loss of atoms, okay? Now, another piece of important information I want you guys to write it down is, for FCC right now, gamma 110, gamma 100, and gamma. So if you do your due diligence to calculate the surface energy, we have gamma 110 that has higher than 100, and then higher than 110. So again, that if you try to materialize that crystal graph into your brain, you actually, it's very straightforward. That totally makes sense, right? You have a more higher, because 111 is more compact, right? It's packed. So the surface energy is definitely going to be lower compared to 100 and 110. Okay? And BCC, you have gamma 111, gamma 100. Right, so again, 111 has higher surface energy. So in other words, for BCC is contrast, right? It's very different. The BCC for 111 has the highest surface energy than 110. Okay, so something you just bear that in mind. And if you're not convinced of the number here I provided, you can go ahead and just, for your practices, calculate each of these surface energy by yourself. Okay. Okay. So by the end of this lecture, these notes I will compile and then upload again on Moodle. So you'll, if you didn't have a chance to catch up what I just kind of talked about, you're more than free to review the video report and the document that I just uploaded. So I don't think there's really, you don't have to be in the pen mode right now. All right. Okay. So questions? I'm actually really slowing my pace, all right, because I'm like giving you guys time to process. All right. Another questions I'm going to ask you related, and I think this is really important, is about diffusions, right? Because on the phase transformation chapter 2, we talk about diffusions, the fixed first law, the fixed second law, and etc. Right? I think there's a lot of, they can be easy questions, they can be difficult questions. One other thing I just want to kind of share or talk about is particularly this one. For those that has a material background, I'm sure that this question is not new to you. Are you surprised that a lot of you guys, when I ask you to calculate, when you calculate, you still get it wrong. And I think there's a lot of attentions and carefulness that you have to really look into these questions, okay? So I'm gonna go ahead and read this, okay? So you have a thick plate of iron and copper alloy with an initial composition of 0.1% of carbon. The plate undergoes a carbonizing heat treatment, 1150 Celsius for 8 hours. So remember, it's 1150 for 8 hours. 0.1 weight percent of carbon. Now, the surface carbon concentration is 1.5% of carbon. At what distance from the surface is the composition of 0.55 weight percent? So an arrow function. So in the final exam, I'll provide you the arrow functions and the constants. So first, you need to calculate the diffusivity of 1150 Celsius using the appropriate choice of diffusion coefficient from the table that I provided as below. So you need to be able to read what I provided the information. So FYI, in the final exam, actually I won't be here in class. I will ask my graduate students to come here and then give you the test questions and you do the calculations. But over here, all the instructions are fairly clearly, instructed. So you have a table that's over here. You have the diffusion species. So diffusion species meaning that the atoms that we are supposed to diffuse into the bulk material. That's the host, right? So the host metal is the bulk material, right? The diffusion species are the species that's going to diffuse into the bottom material. Okay, is that clear? Hey, by the way, is every year we have half of the students that use the wrong. So right now we're diffusing carbon into iron. I mean that's very clear. But a lot of times what happens is partially half of. I won't be surprised half of you guys ending up using diffusion as iron, and then iron as the host. So make sure you see it very clearly. Now, what it says is that it's doing at 150, right? So if you look closely, is that I provided you two columns. One is the carbon, and then the alpha iron, right? The carbon and gamma iron, right? And the diffusivity is 6.2 and 2.3, and you have the activation energy that's provided over here, right? So then you probably, if you see that questions, you will quickly raise your hand and ask me, right? So Professor, which one should I plug it in, right? So the short answer is I'm not gonna answer that because over here already clearly stated which diffusion species I should use, right? So all the information is clear. So it's 150, right? So if you remember your phase diagram very well, particularly for iron carbon, what is it? What host metal should be? Is it alpha or gamma? Is it alpha or gamma? So if you remember your phase diagram very well, so I'm gonna just go ahead and throw you the answer. So if you look at this phase diagram, I said 1150 is 1150, like 1150, right? So it's approximately over here, right? Right? And then I forgot what's the carbon percentage that you're doping, right? So it's supposed to be positive, right? It's not in alpha. Alpha is over here, right? Alpha, right? So I already say 150, right? So it's very clear. The instruction is very clear. So what the right answer that you should have used is this one. Okay? Do you have any questions? Is that clear? I think it's very clear, right? So again, by the time next 3 weeks later when I take that back to the exam, I shouldn't have people using the wrong plug-in numbers, all right? Let's just get this very straightforward. If you're wrong, the mistake is on you, not me, right? I already video record this, right? So that's not my problem, right? So don't complain, all right? Now, another thing is I often get it wrong is this over here is KJ slash, right? So KJ, so what does K mean? K is 1,000, right? So over here is, you should automatically, whatever that number to provide, you say, we already know it's 148, right? So it's 148 times 10 to the power 7, J divided by 1, right? So it's just consistency, right? So because the unit we're dealing with is J per mole, and it's all constant 8.314 J divided by mole times K, right? So it's J, not kg, right? So you should automatically times 10 to the power 3. Another quick thing is that I say 8 hours, right? So 8 hours meaning that how much is that in minutes and how much is that in seconds, right? Because when we're dealing with this, is that all the unit is supposed to be either in joules, moles, K, and then seconds, right? It shouldn't be an hour. So I'm gonna go ahead and calculate that for the sake of practices. So D, you should know that on your back of your head, is D times E naught exponential minus Q divided by R. Right? So we already know E naught is 2.3 times 10 to the minus 5. So times exponential. So the activation energy at this point, you should know that is 148, right? 148 times 10 to the power of 3. Okay? And R, you already know that, that's the constant, right? 8.314. And the T, you also know that, right? It's calculate that, you should get 8.4 times 10 minus 11. So S is again second, okay? Okay. So now we want to know the distance, right? So if you remember your earth function is we want to know is 0.55 minus 0.1 divided by 1.5 minus 0.1. 1 minus earth divided by x divided by 2 times 8.4 times 10 to the power of minus 11 times 28800. So why is it 2880 is because you have 8 hours, so 8 hours, right, times 60 minutes times 60 seconds, right? You get 28800. Right. Now, if you have any questions about how I have taken these numbers and input into the earth functions, I advise you to review the previous note that I talked about. Okay, so why is it 0.55 minus 0.1 divided by 1.5 minus 0? Like, what is that equation? Like, I advise you to review. So today, for the sake of time, I'm just gonna go ahead and provide you all the numbers and how I do my calculations. All right. So these are already fixed equations. So if you go ahead and calculate that, do some simplify and math, you get on the left-hand side 0.68, and remaining earth is x divided by 2 divided by 2.4 times 10 to the minus 6. Okay? So I'm sure that for those that have taken fundamental materials or you have material background, is if you look on the previous slide, I should give you, so in the test I'll give you the arrow function, right? The tablet, right? So the tablet where you can find what is the numbers that's supposed to be inside the hoop. Okay? So there's some math you have to do the proportionalities between 0.68 and find that table number between that and calculate what is supposed to designate x. One quick hint for you guys for the final exam is these numbers at the end that you calculate, usually they're pretty well rounded up, right? So again, like each of these questions where you calculate, if you get like minus of 10,000 power of 11 or something that you must have calculated wrong. Because for the sake of me, I will go over each of these test questions. For the sake of my time, I will keep every number very simple. It's like 2 or 3, 11, and then I'll go down. So if you get a number that just doesn't make sense, you must have calculated wrong. All right? So if you look at this and then you go back over here, is you should find, right? So 0.7, so I think it's 0.71, right? So over here it should be 0.71. Then you should know the z, right? So you can do some proportionalities to calculate that, and I'm gonna leave that homework to you. Okay? So x divided by 2 radical 2.4 times 10 to the power 6, you get 0.71. Okay, so if you use the tables informations and then you do a proportionalities, you should get 0.71, right? So with that, the x should be final answer 0.2 meters, right? Meters, okay? So that's 2 millimeters. So in the test, if you get the unit wrong, I'm going to be very cool on this is that you lost the entire point for that question, okay? So if the unit are wrong, everything is wrong, all right? So there's no, I'm not going to give you any grace on this that, hey, you got the answer wrong, but the unit was wrong, and the unit are missing a square or units. If the units are wrong, you don't provide a unit, you automatically lost the entire test question score for that section, all right? Is that clear? So no complaining, all right? Or if you have something to say that you feel unsettled, you're more than welcome to come and talk to me, explain to me why by missing a unit, you should get a partial point for that. I'm sure that in the future, if you're engineering, you're not dealing with any life matter stuff, and your product comes up from you doesn't really care about units. And if that's the case, that's different cases. I'll give you the full mark for that. Right? But hey, I'm keeping my ground for that. Units needs to be correct. All right. So let's do that. Okay. Be professional. All right. I'm not trying to be sarcastic, but be professional. All right. So you can either write it 0.002 meter or 2 millimeters. Right? The answer I'm looking for is 2. Right? And with units. So I think the question is just really easy. I don't know if it's easy to you or not, but if you do your homework, it's very straightforward. All right. Any questions so far? No. All right. So I'm gonna move into the next section. So solidify. So this is another big chapter that deal with some physics and math about how solidify forms, right? So mostly deal with metals, and that also combines combined mostly with thermodynamics and phase structures, phase diagram, etc. So here again, I'm just reviewing. So you can see below is a casting solidifying from outside to the inside. And a section of solidifying casting may be considered as a bottom figure that we withdraw from a surface. So I think the previously when I was talking about the chapter in solidification is that a lot of these from liquid to solid to solidify it's like a gradient, right? There's a proportionality when it starts from either a surfaces or claim that it start nuclei and then form that structures, right? And also that deal with if it's a homogenized heterogeneous nucleations or homogenized nucleation or heterogeneous nucleation, right? So at this point, if you have a plane, like a monoid here, it provides the nucleus to have a more smaller energies for form the heterogeneous nucleations than homogenized nucleation, right? So that's why we have solid that form always on the surface mode and saw nuclei form dendrite. Okay, so one of the great example I give in the past in my lecture is ice cube that you try to refrigerate in your refrigerators, right? And if you look closely, is that you always have the ice that's formed on the surrounding cup, and then form a somewhat a dendrite features, and then start pushing the water into the middle, right? And then if you look closely enough, and you're being absorbent, you will see all the bubbles and all the contaminant trapped in the middle. And eventually, once it's solidified, you have all the bubbles and air, gas that trapped in the middle. So the same analogous is among all the same other metals as well when you liquidize and then solidify, right? And this is a great example, right? So what I'm doing is I'm gonna take a section out of here and then pretend like this section pretend I can do that. And use this as an example of drawing the section out if I have the ability to draw a section from the liquid and then pull out as a circular ball, all right? So here you can see is I'm considering a copper with aluminum. So throughout the lectures I use either aluminum, copper, aluminum, doesn't matter. And so the purpose is I'm going to use an alloy. So you have some additional. So in this case you have 4% aluminum. And so now in the alloy in addition slowly pull from the dish from the melting point. So again, same as that one, I draw sections, duplicate that image in your brain, and then over here is the same section over here. It's inside the mold right now, liquid, right? And I'm slowly drawing out this liquid solid stuff, right? So one of the interesting phenomena is that if you understand the phase diagrams, usually you have eutectoid, and stuff like that. You have the phase diagram, and then you have like alpha, gamma, beta, and theta, right? So it's because of the alloy, right? So if you can imagine that phase diagram in your kind of back mind is that when you start drawing, right, it is understandable on the solid side, you will have a gradient, right? You will have a gradient, okay? Because if you draw out, right, you will have a gradient according to the phase diagram. Because when you designated a fixed concentration, say 4 wet %, the phase diagram, regardless of what it is, when you start pulling down, it will go through alpha plus liquid region, right? And then slowly coming to alpha plus beta region. For the sake of argument, right? Alpha, beta, alpha, gamma, right? So if you go past the alpha liquid region, right, you will have a gradient. Alpha is a gradient, right? And then when you start drawing, that gradient will change throughout, right? So one of the example I was talking about is if you were able, a lot of people end up in a semiconductor, factory, is that the way they make a very purified 99.99% silicon is actually very similar to this process, is that they have a purified seed on a particularly plane directions, and then they start drawing in a liquid mode, and then try to pull out. So the more they pull out, the more contaminate, or the other purified, other elements is going to be thrown back into the liquid, and then you have a more purified solid at one end compared to the other. Right, hopefully that makes sense. Right, so here is a diagram. I didn't find it, still haven't had a chance to put, so this is, just pretend this is aluminum. So if you slowly cool down, so this is 4 wet %, right? So if you slowly cool down, you encounter alpha plus liquid region, right? Okay? So I'm gonna go ahead and then use this diagram. I'm gonna enlarge that a little bit, bigger. So this is the same diagram. So C naught. So this is again 4 weight %. Right? All I'm doing is just enlarging this diagram from the previous one. So if we cool down, so over here, this is the the composition of the liquid line, right? And over here, this is if you look at this is the solid line. Right? So this is the solid line, right? And this is the designated composition. So that's it, right? So the farther we cool down, right? If you draw a tie line, right? You get a different sort of a composition. So CS blah blah, CS blah blah, right? And the point I'm trying to make is that this will always be a mass conservation, right? Regardless of what, at a certain point that element's concentration it is, at one point the liquid must balance the entire copper plus aluminum composition. So one thing is that when you do your calculation, the mass needs to be conservation, right? There's no, like if you have particularly one end, you have a very high copper. At one end you should have higher aluminum, right? So, and this is the weight % of aluminum. Right, so CS, as I've proven previously in my lecture, is equal to KC naught, right? So K, I'll explain that a little bit more. So we should know that KC naught equals to CS. Okay? Okay. So few things, again, this is already on previous slide. So let's assuming the solid is solid, a fancy way of saying, and liquid is find that K equals to CS divided by C dot. So K is what we define segregation coefficient. So if K equals to 1, meaning that there's no segregate, there's no precipitate or anything like second phase coming out, right? So you always get like a 0.1, 0.6, or 0.7, right? That's the entire point of alloy, right? So you want to know what is the K value. So again, if K equals to 1, there basically is either a pure alloy, like a pure alloy. There's no segregation. But let's have a break, and then for you guys, please check your Moodle right now to see if there's any